So we're doing hashing today, right? It's a hash table. See, there's the S's and the H's and stuff. Yeah. So, okay. So, So one thing is provably fun, right? You did a lot of. Remember hashing? Have you guys seen hashing? Yeah. So in some sense, this happens a few times in this course, where I say, "Oh yeah, shortest path," or depth first search, and then people tune out because they say, "I know this," and then the test comes and problem, I don't know, 2A2, nobody gets, right? This is the one on depth first search, understanding how it works. So there's sort of a disconnect, right? There's this, oh, I know hashing, but in this class we sort of go beyond and we go and we prove things, right? We really understand what's happening at a level that is, well, in some sense beyond 61B. So while the data structures may look familiar, what we're doing now is sort of tying up some of the loose ends around there, but really one could call it tying up loose ends, or one could say, well, we're telling you what's really going on. So depending on your point of view. So so one aspect is this is hashing, and this is going to be the 61B level explanation that's in the first slide. And so you keep a list. That's in 61A. You do theta and search. You could do a binary search tree. So you want to maintain a set of IP addresses. Why do you want to maintain a set of IP addresses? You're a router, and for each IP address that went through the router, you want to keep a record of it. Okay, this is a very natural thing. Okay, or you're a web server. You want to keep a track of all your clients. So you can keep a list, and it's order n, search, right? And the reason the 250 is there is because you don't want to have all the IP addresses, right? You just have the ones that you saw. Okay? So there's a binary search tree. You can keep a subset. You can tell whether something's in your subset using a binary search tree. This is theta of log n, insert and delete. You can keep them in array. So what you do here, keeping them in array is kind of funny. You can't have an array of 250 items with IP addresses. You can push and keep them in the end or not, but this is sort of like a list again. What you want to do is look in a particular place in the array that corresponds to the IP address to see how it's going there. So what you want to do, this is really what hashing is you're storing the entries in some sense in an array, but the problem is that there's many IP addresses, and you only want to have an array that's of size around the number of items you're going to keep. Okay, so you could just allocate an array that's 2 to the 32, and then just look it up in the array there, and that's trivial because there's 32 bits in an IP address, and you can just look up that bit and see if you set it or not. Okay, but that's not what hashing is. Hashing is sort of mapping each IP to a place in the array that then you could look up and order one time. Okay. So the example is you have this universe. You've seen this figure is slightly modified in the first slide. You have some elements X, Y, and Z are your IP addresses. IP is Internet Protocol addresses. Do people know what IP addresses are? Yeah. If you do ifconfig, if you have Linux, you can do ifconfig and it'll show you your IP address. If you have Windows, I apologize. Okay, so h of x, so you're mapping it. In some sense, you're mapping each IP address to a position in this array. So this hash function is mapping from this universe to the size of this table, essentially. And you can see what you could do if you map two things to the same array. Some unpleasantness occurs. The unpleasantness here is that you have to build a list, right? And so then when you look up, if you look up X, you have to scan over the list, and you have to look at Y, and you didn't want to see Y, and it's like, just why did I have to see Y? But why is it bad? Is because you're scanning over these lists of longer length, right? Okay, Z is also here, and so on. right? Z is something better happened. These things did not collide. I'm going to use the word collision a lot. X and Y here collide, right? In the hash table, they are mapped to the same place. So that's a collision in the hash function on this set of keys, okay? So you can pick hash functions in a lot of ways, right? So this is, there's 4 bytes in an IP address. You could pick the last byte. But what if you come from a place where all the IP addresses have the same last byte? Okay, maybe some last bytes are very common. Okay, well, you could use the first byte. Yeah, okay, well, obviously the same problem, right? Here, for example, Berkeley, all the IP addresses in Berkeley have the same first 2 or 3 bytes, I think. We have a lot of IP addresses. We could do various things. We could add the bytes up, divide by 2, add 3, and shift by 10. Okay, that's something. Now, let's think about this hash function. Or don't think too hard because the details don't matter. It just says do something with all the bits, right? That's what it's saying. Okay, but can this hash function be bad? Is there a set of elements where okay, what does it mean to be bad? Okay, what does it even mean to be bad? How do you say a hash function is bad or good? Yeah. Yeah, something about, eventually we have to define it. And he's trying to get at, oh, okay, what do we need to decide? How do we even set up like I said, this is about proving things. So we need to prove certain things in a certain framework, right? Can this hash function be bad? Well, in some sense, I'm going to tell you this on this, I'm going to explain in more detail, but I want you to think about it a little bit on your own, or at least with a little bit of guidance. How many IP addresses are there? 2 to the 32. Now, if I look at all those IP addresses, and I map them, no matter how I map them, to a table of size 100, is one entry going to have a lot of IP addresses mapped to it? So once you'd show me the hash function, I could always find a bad set of IPs. I could just pick, I know there's some, on average, each entry has a fair number of items mapped to it. So I know I could find a bad set of IPs. So every hash function is bad in this sense. So in particular, let's look at this and say, do this argument again. There's a lot of IPs. There are 250 table entries, which is roughly what we see. So what's the average number of keys mapped to an entry? Is it 250? Is it around 160,000? Am I really asking you to do this division? Because I can't. And so that was a joke. But the answer is it's 4 million, right? The average load, if you think about mapping all of these IPs to 250 entries, is this number. And there's a 4 and a 250, so you're clearly going to get a 16 somewhere, a 4 and a 1/4 or something. I don't know. It's also, but it's a lot. The point is a lot. There's no good hash function, right? There's no way to do this in this model, right? There's always a bad set of keys for any hash function you choose, which is what you saw me, the exercise I did with the first byte, the last byte, or this other thing. Doesn't matter, right? No hash function is really good. Okay, so, and this is true for any hash function. So that last complicated hash function is no good in a sense either. So what do we do in theory, right? Now we're done as a theorist, right? We're glad that all the hash functions suck, as a technical term, suck. Meaning that in this case, it means I can find a set of keys which is bad for it easily. Right? For every hash function, there's lots of sets of keys which are bad for it. So the solution, well, what if we thought of the keys as random? Now the probability that 2 keys collide for a table of size n is which one? Which one of these is it? Two guys need to collide. They need to collide, right? I say x and y, they're 2 guys, 2 IPs. I'm mapping the hash function of one and the hash function of another, and now if those hash values have the same value, that's a collision. That's what we saw on the first slide for x and y. What's the probability? Yeah. Okay, yeah, it's 1 in n. The first one goes to some entry. You don't care where the first one goes. Now, if you think about the second key being random, okay, and it just being mapped to a random location, the first one went to some entry, and there's n entries. The second one is equally likely to go to any of the entries. So it's the probability it goes to the same entry as the first guy is 1 in n. Okay. Okay, does that make sense? So, I mean, like, a priori, I might have said 1 in n squared if I was doing this fast, right? Because there's n squared possible choices of where to pick both of them. But, in fact, n of them are bad, right? Both of them could be picked in the same place. So this argument is a little bit, it's not completely, it's completely obvious after you see it, but there's wrong ways to go. The 1 in n squared was not an unreasonable answer for the wrong argument that looks like it might be right. Okay, these things can be a little tricky. Okay, so random keys are good, but we can't just assume the keys are random, right? There really are patterns in your data, patterns in how IP addresses are assigned that might be bad for your application. Okay, so now what we're going to do is the following. What we're going to do to make this okay in our world is we're going to use randomness, but we're going to instill the randomness. Okay, we're not going to rely on the world to give us the randomness. This is a big trick in computer science, our use of randomness in algorithms. Okay, we're going to let somebody else pick the keys. They can pick whichever keys they want. We have no control over that, okay? But then we pick a random hash function afterwards. What we do is you pick your keys. I don't care how you do it, but I'm not going to show you what my hash function is. So you can't pick keys that are bad for my hash function, okay? That's the idea, okay? So in real life, hash functions are built first, right? You have a program, and then you're using them. But this sort of models the world that, yeah, the hash function picks its, the computer sets itself up with a hash table and a hash function in that table. You're not trying to attack it. You're not trying to engineer a set of keys that are going to kill the hash function, right? Typically, you don't want your program to work badly. So, okay, so this is the assumption. Is the set of keys does not depend on the choice of the hash function. It's not so much that it has to be done after we know what the keys are. We're not going to really look at the keys typically. What we're going to do is pick them randomly, independent of the keys. We don't, okay? So that's the idea. So we might choose a random hash function, but the keys that are allowed to be presented don't know what that hash function is. Okay, that's what the idea is. Okay. So what do we need to do here? Now we're in control of the randomness. We're not relying on any randomness from the world. Okay, so we are going to choose randomly from a bunch of hash functions. And one of our hash functions is choose the first byte. Okay, that could be one of our hash functions we could choose at random. Or choose the last byte. Or choose that middle crazy thing in the middle. Okay, so we want to have a rich set of hash functions to choose from. Okay, so a bunch of hash functions. Since we want to make it, since we're going to make it all formal and stuff, we call it a class of hash functions. Okay, so we're going to pick, we're going to say there's some keys out there that can be anything, any subset of the universe. And now I have a family of hash functions. I'm going to pick one of my hash functions randomly. Okay, so here's an example. Okay, so I'm going to let the number of entries in the table be 257. Which is a prime. Okay, so I'm picking a prime, and you'll see why in a minute. And now I'm going to say a hash function is specified by 4 things, right? Like 4 numbers. And 4 numbers, A1, A2, A3, A4. And the hash of my IP address, remember the IP address is 32 bits, or 4 8-bit bytes, 4 bytes, okay? So a byte is 8 bits, if anybody doesn't know, okay? So the first byte is x1. And the key for what the key here is x1 is in the range 0 to 256, right? So it's sort of it's a number modulo 257. It's a valid number modulo 257. That's what's going on here in this choice of hash function. Okay, that's why we have 4 of them. We want to make sure that each of the things we're working with, this A1 through A4, are in the range from 0 to 256, and our inputs are kind of nice. We can actually break it down into the number of bits we need, and each item here, xi, is a valid element modulo 257. Okay, so it's a class of functions, right? So this is a class of functions. If I tell you A1 is 1, A2 is 1, A3 is 3, A3 is 1, and A4 is 1, that's specifying a hash function. Those 4 numbers are specifying one of my hash functions from my family. Okay? And in particular, the hash function you get out of this specification is this. You're just adding up all the bytes mod 257. This is a very natural one. Okay, so how do you get the first byte? What would be the hash function? What would be the set of A's that gives you the hash function that corresponds to the first byte? Okay, by the way, this is how you this is the hash of this particular function. Sorry, I got this out. But if you want to apply this function, you're just adding up the bytes. Okay, so 100 is the first byte. A0001 is the last byte, right? So this class of hash functions covers this first byte or last byte or middle byte, right? It's sort of more general. Okay, so a hash function from a family is the same. Now we have this whole huge class of functions and the functions all have the format that they map this 4-byte thing to 1 byte, essentially. Okay, this big universe of IPs to our table, to the table indices. Okay, so it's just so this is called a hash family. Okay, and now how do you select a random hash function from this family? Yeah. Yeah, that's all you do is just pick randomly A1 through A4. Exactly, right? You were all dying for me to move on, right? You should all understand it. So how do you pick a random hash function? You just pick A1, A2, A3, and A4 randomly. Okay, and you get one of these functions. Okay? Okay. Is it good? Now, how do we tell whether it's good? So we don't know whether the hash, so for a particular hash function, one hash function is good. Now you get to look at the keys. Okay, when you say, is it good? You say, well, for a set of keys, any set of keys, when I pick randomly, is it going to do well for that set of keys? Okay, and you know for any hash functions, there's a bad set of keys, right? So now the question is, well, how do you set this up? Okay, so what is good? First, we should say what is good. Remember, for random hash functions, the probability, we want to evaluate the probability of collision. That's how we decide what's good. Just if the probability of collision is low, that's good. So what is a random hash function? It's 1 over n, right? We don't want collision. And a random hash function seems to be as good as we can do. Okay? So, okay. So now we're going to calculate. These are 2 values, x and y, and a collision is where h of a of x is equal to h of a of y. Okay, that's what a collision is. You have 2 keys, x and y, okay? They don't equal each other, so you'd like them to be in different places in the table, right? But the hash function maps them to the same place. Okay, so there's this funny intervening thing where we pick a random a. Okay, so we're saying x and y can be anything. They can be worst case. Any adversary can choose x and y. And now we want to argue that after they choose x and y, when we pick a random hash function, the probability of x and y colliding is small, right? Okay. So what do you think it is? What? Right? 1 over n is what we should be targeting, right? Okay, so this is the, now it's mathematical, right? What we're saying is, look, you're giving me any two elements of this field from 0 to 257, any two, x and y. Now I want to calculate a bound on the probability that a randomly selected function, which is correspond to a1 through a4, maps x and y to the same value, right? Okay. Okay, so so what we're going to do is we have two x and y. They're different, okay? Meaning that at least x1, either x1 doesn't equal y1, or x2 doesn't equal y2, or x3 doesn't equal y3, or x4 doesn't equal y4. Okay, so for now, let's just assume that x4 is not equal to y4. You can change the index if you want. At least one of them must be different, right? X does not equal y. If they equal each other, the hash function better map them to the same place. Okay. Okay, so now we're going to go ahead and say that A1 and A2 and A3 are chosen first. We're not even going to worry about the randomness for them. We don't, they can be chosen by anybody, but we do choose them randomly, but they're chosen by anybody. So now, what do we need? So the bad thing is when this hash function maps x and y to the same thing, right? That's what this says, and that only happens if at some point when you write down this hash function, you get a1 through a3, a1 times x1, a2 times x2, and a3 times x3. Let's just call that x, big X. And correspondingly on the right-hand side, call big Y the sum of the first three terms on the right-hand side in the second line. Okay? So now what we need is A4, we're going to use the randomness in our choice of A4. That's the randomness we have left. We're not worried about the randomness in A1 through A2. There's something, we don't care. We're not going to take advantage of that. But for A4, we know we're choosing A4 randomly from 0 to 256. Okay? Okay, so how many values of A4? Now, this is where you can see values. How many choices do we have for A4? 256, or n, right? N choices. Okay? Okay, so now how many satisfy them? Well, A4, we could just solve this equation for A4. You know, how many values of A4 satisfy equation star? That's just the same thing as solving the equation for A4, right? Okay, so A4 is equal to x4 minus y4, and so x4 minus y4 has a multiplicative inverse. Okay? So you could get A4 is equal to the y minus x times the multiplicative inverse, right? So this tells us how many values are there for A4? Is there a set over here, or is this just one value? A4 equals this number, right? So there's only one value where the left-hand side is equal to the right-hand side. Only one choice of A4, okay? There's only one value of A4, right? Because these things have inverses. x4 minus y4. Why is this not 0? 0 doesn't have an inverse. Why is this not 0? Yeah, we assume that x4 is not equal to y4, right? So it's 1 out of n choices. 1 in n, which is the probability of collision. So that's good. So the answer is A, right? Everybody sees this? We proved it now. Okay. So that's great. So this says it looks like the keys are random. Okay? Or it looks like we're placing them at random in the hash function, hash table. Why wouldn't we just place them at random in the hash table? Why wouldn't we do that? Doesn't that seem like all I'm trying to do is get to random? Why don't I just use an actual random hash function? Just each element, I put it in a random place. Yeah, you don't know how to find it. Yeah, that's a problem, right? So the whole point is you do have to have a hash function that's easy to compute. Okay? And the randomness here is our randomness. This is us. We're using the power of randomness. The computer scientist is fighting the world by injecting our own random bits, our own random choice of the hash function. Which seed do we use? It's our power to choose those A1s, and that's what we're doing to combat. The average case world is nice. If all the keys were random, it was nice. But if we were trying to combat sort of biases and worst case behavior, this randomness helps. Okay. So in general, for universal hashing, you want to choose a hash function uniformly at random from family H. And what we did here, the hash family is universal if exactly 1 over n of the hash functions map any pair x and y to the same value. Okay. So in this case, this particular hash function worked for 32 bits to 8 bits, right? The universe was the input to the hash function was the universe of all 32-bit strings. So maybe you have a bigger domain size. Maybe you have 64, and you still want to map it to 8 bits. So you can do this with a larger tuple, right? Instead of having, if you want 64 bits to 8 bits, then you would have 8 numbers you choose at random. Okay. So this is universal by the same argument as above. Where I used A4, you can use AK. Okay. Here, and it has to be prime here again. Okay, so another universal hash function, that gets to be complicated because it seems like for every universe you have to do something that's designed for that universe. Here you can this is another universal hash family where what you choose at random is A and B, okay? Where you choose A not equal to 0. Because why don't you want, really, you sort of don't want A to be 0. Why don't you want A to be 0? Yeah, because it won't depend on the input if A is not 0, if A is 0, right? All elements will be mapped to the same thing. In fact, the previous set of hash functions have that undesirable property too. If you pick all the AIs being 0, then your hash function is not very good. It maps all the items to 0. So, but that's fine. It still meets the definition of universal hash functions. It's just you really hope you don't choose 0 because that would be bad. But okay, so here you need this inner. So what we're doing is we're taking mod p inside, and then we're taking mod m, which is the size of your table. So mod p, that p should be bigger than your universe. So the first thing you're doing, the intuition of this hash function is the first thing is kind of randomizing the position of x. It's putting x in a random position between 0 and p. Okay? Right? When you multiply by a and then you add b, you're sort of taking x wherever it was and moving it around a little bit. Okay? And the last thing is just bucketing, mod m. You're putting the 0th and the mth and all those items together. Okay? So m is the size. Here you can read p as just something that allows you to do this modular arithmetic that sort of makes it makes these functions where you describe them with a and b makes you be able to argue about these functions, and I'll argue about them in a minute. And then the last thing is just modding out to the right side of the table. So so the first step, now again, what's the probability over? Is it the probability over x and y? Is our probability distribution over choices of x and y? No. Our probability distribution is over choices of a and b. Okay, x and y can be anything as long as they differ. Okay? Anything in the range 0 to p minus 1. Okay? So now, given those, so this probability is in this notion of the sample space being the choice of a and b. Okay, so now ax plus b, now we're going to say, we're going to use this sort of claim. What is the probability that ax plus b equals r and ay plus b equals s? What does that look like to you? Is that 2 linear equations, right? And what are the variables here? You can interpret the variables as being a and b. X and y are fixed, and r and s are fixed. Okay, so if I fix x and r and y and s, the variables here are a and b. So if these things are linearly independent, how many solutions are there? One solution, right? So only one of the possible pairs a and b will actually solve the set of linear equations, right? And how many pairs are there for a and b? P minus 1 times p, right? Because you can't choose 0 for a. You can choose any other number from 0 to p minus 1. And b, you can choose any number from 0 to p minus 1. Okay, so that's the sort of argument from, this is why it should be clear immediately when I say this, what's going on. It's a linear system. There's a unique solution. Okay, and this is the argument. First of all, we know that r is not equal to s because why? Why is r not equal to s? Because a is not equal to 0, right? If a is not equal to 0, then the b and the it's a times x is going to be different than a times y, right? Also because it's prime, a has an inverse. Okay. So r has to be different than x because b is the same. Now every r and s corresponds to exactly one a-b pair, so that's 1 out of p times p minus 1. Okay, it says that r is different than s. It's just the same system. It just says it's a system of linear equations. There's one solution. So this probability here in blue is 1 over p times p minus 1. Now, how many r and s's have r equals s mod m? Well, for each r, you just add m to it, right? And so that can happen p minus 1 over m times. This is just how many buckets are being mapped to the same value. So that's less than p times p minus 1 because there's p values of r, and this is a floor, so it's less than this value. So that tells you we get this value. The probability, the ax plus b equals r, and ay plus b equals s, and multiply, that's a probability for a particular one. And of those, this many are mapped to the same place. That's what fraction of r and s is mapped to the same place. So you multiply them together, and you get 1 over n. Okay, so this is also universal. Okay, so it's a very nice universal hash function. It works for any value, any number of bits. Okay. Okay. So now, in terms of now we're going to move to slightly. That was universal hash functions. In general, all these arguments are what we're going to now do is we're going to kind of punt a little bit for a little bit. The next lecture we'll come back and really use universal hash functions. Now we're going to think about random hash functions, because I've shown you that we can construct families of hash functions and choose our randomness internal to the computer so that we can make the world look random with respect to hashing. Okay, at least with respect to some behavior. Okay, so now we're going to go back to this world where we have a random, we think of items coming in at random, or the hash function is random. So in this world, hashing looks sort of like this. You have n balls, and you throw each ball uniformly random into n bins. Or in some cases, you have n balls, and you throw balls uniformly at random into m bins. Okay? So what's the maximum bin size for this example? Does anybody know? Log n. It's theta of log n. It's actually less than that, but I'm going to show you theta of log n. O of log n. It's O of log n, but it's less than that. It's O of log n over log n, but I'm going to show you something weaker. Okay, so and how do you show this? We did this in 70. This should not have an equals there, but the probability that a bucket has more than k items in it is what has to happen? Well, k items have to go in it, right? So some subset S of all your numbers of 1 to the subset S of the numbers 1 to n, the numbers 1 to n is the balls. Okay, some subset of the balls need to fall in your bin. And the subset of the balls, those balls have to be of size k, at least. Okay? If some bin has more than k items, that means you can just name the balls that are in there. Okay? Now, how many possible subsets are there? Well, there's n choose k. Yeah, there should be something here, but let's just skip to the last line. There's n choose k subsets of size k. And now for each one of those subsets, every one of those items must have landed in this bin. What's the probability that each one of those items landed in the bin? It's 1 over n. And there's k of them, so it's 1 over n times 1 over n times 1 over n times 1 over n. So it's n choose k times 1 over n to the k. Okay? That's an upper bound. Okay? So there's other ways to do this calculation, but this is an upper bound. This says, look, this event, this bad event, where a lot of balls fell in this bin, I could blame it on these k balls. And I say there must be these k balls, at least one of these events that some k balls had to fall in. And the n choose k is like the union bound. We're saying for every choice of k balls that could fall in this bin, what's the probability that all of those k balls fall in this bin? Okay? Okay, so now I've changed the word a to some. Now we want to say what's the probability that any bucket has more than k balls falling in it. Okay? Any bucket. Or some bucket is any bucket. Well, I just multiply the previous expression by n. Because now we're looking at n different events. Each one of the events corresponds to a different bucket. And we can use a union bound again. It's less than n times the probability that one of the buckets is bad. And the probability that one of the buckets is bad, the previous argument didn't matter which bucket. Okay? So it's this expression. Okay, so this expression is a bit ugly, and you can do you can just grind out these calculations. And choose k is less than n times e over k. You can sort of think about why that's true, because the top is n times n minus 1 times n minus 2 down to n minus k plus 1. So there's n terms in the bottom, there's k terms in the top. So this should be to the k. That should be n over e to the k. And so you have sort of a power of n to the k in the top and a power of n k to the k in the bottom. And the e is there because the k is decreasing from k to 1. So then you just start plugging in values and trying to make this small. So if you use that approximation and the fact that k is greater, and use some value of k, which is greater than 2 times e log n, then you get a bound of less than 1 over n. Okay? So what this says is if you plug in this 2e log n, it says the probability that some bucket is greater than 2e log n is less than 1 over n. Okay? So the maximum, so the probability that you have a very large bucket, meaning larger than 2e log n, is less than 1 in n. And it's better than this. It's just a rough analysis. Okay? So the maximum bucket size is at most this, with probability 1 minus 1 over n. So very close to 1. Okay? Does that make sense? Okay, so this is what computer scientists call with high probability. With high probability means, now you can't really have high probability. You can't have probability of 2 or 3, right? Because probabilities only go up to 1, right? That's one problem. So what does high probability mean? It means very, very, very close to 1. Okay? So meaning the term that you can, how far you are away from 1 goes to 0. Okay? So that's what with high probability means. You can force it to go to 0. So this thing, I can change this constant from 1 over n to 1 over n squared by changing this constant to 4. Okay? So it's just a game we do. So now this was the state of the art. This is a very, very natural, you could imagine somebody, one of the first things you study in probability is what happens when you throw balls in bins, right? And they analyzed all this, 100 years ago or more. But recently, in the last 20 years, maybe 25 now, I'm getting older, they developed this better process, okay? And it's fascinating that it can do a lot better, okay? So what we're going to do instead for each ball is instead of throwing a ball in each bin without looking, that's just like, I'm closing my eyes, whatever happens, happens. I'm going to look a little bit, okay? Just a little bit, okay? I'm going to say, okay, I'm going to throw myself in this bin, and I'm going to pick 2 bins, and I'm going to pick the better of 2. Okay? Not much different, right? I looked a little bit, right? So now I'm saying, instead of each ball picking a bin at random and just placing itself in that bin, or you throwing the ball into the bin at random, you decide, you look at 2 bins, and you pick the least loaded, and you put the ball in that bin. Okay? Sequentially. Okay? What's the maximum bin size? So does it go by, what do you think? Does it go by, it could go by down by half, right? Because it's sort of, you should get some benefit from looking. It should go back maybe the square root of the maximum load? Yeah. Could it go to constant? The maximum bin size? Like, it's hard to understand what this is even going to do, right? Okay, so in this world, you got to think of log n as terrible. It's terrible. It's huge. It's gigantic. I want it to get smaller, right? Log n is what we showed in the previous slide. I want it to get smaller. So one thing, square root of it makes it much smaller, but one thing is taking the log of it makes it much, much smaller, okay? So this particular algorithm, you know, if you pick in any reasonable n, this is going to be a very small number. So like log of 1,000,000 is 20 or 30, you know, that's about what you would expect in a hash table of the size of 1,000,000. This will never be more than 5 or 6. So it's a little shocking, right? It's a little shocking. Okay, so now you have to prove it. How would you prove it? Yeah, you have no idea, I hope, because, I mean, not I hope, but I would presume, because it's not that easy. But it's easy after you see it, but, you know, it was only done a few years ago. So the idea is you think about a random sparse graph. Okay, where's the graph come from here? Where's the graph come from here? Yeah. Yeah, each ball chose 2 bins, right? So there's a natural graph here. Your vertices go bin, and the edges are balls, right? And the edges are picking 2 bins, so they're their edges. And it's sparse, so it's average degree. You can make it sparser by sort of having more bins. You can make that degree in some small constant. And the graph with average degree of less than 1, what is that? What's the average degree of a tree? Average degree of a tree? Anybody? How many edges does a tree have? N minus 1, right? And what's the sum of the degrees? 2 times n minus 1, and now if you divide by n, you get something a little less than 2. So so things with small average degree are really disconnected. If it's smaller than 2, it's disconnected for sure, and in fact, it's really disconnected. Okay, so if we just think of half the balls, it's completely disconnected. Not only is it disconnected, each component is tiny, right? Each component is just log n nodes. Okay, they're really a vast space of emptiness, and nobody's friends with anybody, and nobody's connected to anybody, right? This is a very, very sparse graph. So really what you have is not one graph on n nodes, you have a bunch of little bitty components of size log n. Okay, so that's what happens in these random sparse graphs. Okay, so now even more so, you know, everybody's favorite problem on the midterm was this degree of the induced subgraphs. Did people like that problem? Yeah. Okay, so I apologize for that problem. Should I apologize? Let's see. Let's see what time it is. 2:55. Okay. Okay, so the degree of the induced subgraph. Now, what is an induced subgraph? You take the vertices, some subset of nodes, and there are some edges that go between nodes, both of whose endpoints are in that subset, right? And then there's some edges incident to those vertices where one of their endpoints is next to that subset. So the induced subgraph is just the edges inside of the subset. Now you can see that that's very unlikely too, right? If you have a small subset, say 3 vertices, then for an edge to have both of its endpoints in those 3 vertices is 3 over n for one endpoint to hit that vertice, that set of vertices, and 3 over n for the other one. So it's 9 over n squared. So it's very unlikely that, it's fairly unlikely even one edge is in that subset, right? Because there's only n edges. And as you get larger, you need a lot of endpoints, both of whose endpoints are in that subset to have any degree inside of that subset. Okay, so so the whole graph is sparse, and now any subset is really sparse. Okay, there's nobody who's, and this is sort of contradicting the previous slide. The previous slide says there is one bucket, there is one vertice here who has large degree, O of log n. But if you take that vertex and all its neighbors, then their average degree is 1 or less than 1. Okay? Okay, so, so now what you do is in the C of this graph, you sort of think of removing vertices. If you're first you remove the degree D at 10, this is also very familiar with the midterm. That's what the greedy algorithm in some sense. It says if you remove all the vertices whose degree is like less than the average, you can get rid of a lot of vertices. Okay? And for and really each of these guys each of these components are by themselves. They're only of size log n. So every time you remove degrees of vertices from that component whose degree is less than 10, you have the size of the component. Okay? So after log of the size of any component iterations, you've gotten rid of all the graph. Okay? So it removes all the vertices in O of log n time. The log here comes from the fact that this removal removes half the vertices in any component each time, and the log n is the size of the component. Okay, and that process really models the maximum load, because this notion of a vertex, when you throw a ball into a bin, when you choose a ball, you pick 2 bins, and you pick the least loaded bin. Okay? So in the first round, what you would do is anybody who is next to a vertex whose degree is less than 10, you know their max load is 10. Right? Because you look at the graph, only 10 other balls chose this thing. Even if all of them went into that bin, the max load is 10. Okay? And then by induction, you can show the max load is 10 log n. 10 log n. Okay? So it's kind of a fancy argument. This is just a sketch. The first line here, random sparse graph, that's a calculation, very much like we did on the previous slide. It has a lot of n choose k's and 1 over n's and some powers, and you do some nasty manipulation, but it's not hard. It's just like grinding. And then the second one is also a calculation like this. This last thing is a combinatorial argument. So this process really argues that the maximum load is O of log n, which is really, it's such a basic phenomenon that it's surprising it took until so recently it was found. Karp is, who knows who Karp is? Does people know who Karp is? He's a Turing Award winner, professor here for decades. He's a god. Luby is he was also very involved with Berkeley, but he's at Qualcomm now. And Meyer after Heidi, you can guess that he's from Germany. So, okay. Okay, so I'm going to give you a break now. Okay. All right, so I should say, I did want to say this is a deeply interesting thing. What it's saying, or at least to me, it really is deeply interesting. So the idea is like, what if you were just trying to assign balls to bins and you were allowed to look at all the bins? What would the max load be? 1, right? You just round robin. You put the first ball in the first bin. You put the first. You don't even have to look, right? It's very easy to do it without randomness, right? If you're allowed to look. So this says, so throwing balls into bins means you are not looking at all. You're just you're throwing caution to the wind, okay? Okay, you're not even seeing where the problems are. Okay, so this says if you just look in 2 places, then you get to do a lot better in the worst case. Okay, so it's very, very interesting in some sense. If you look in 3 places, you don't do much better. You don't get this sort of, you just get, after that, 3 and 4 and 5, you only get a linear improvement in congestion. So it's also a statement about the value of information, right? Just looking a tiny bit helps you a lot, okay? But getting all the way to N, you have to go a ways. Okay, so now let's say you really, really don't ever want to collide. Say I give you N items up front, and I'm saying you need to pre-build, these are all the items that are ever going to be looked up. You need to pre-build a hash table that doesn't have any collisions, okay? So that's the idea. So that's easy. What you can do is you can just hash the N items into N squared space. Now, with reasonable probability, it's sort of the pre-birthday paradox, meaning it's before you get to the number of items where you get a high probability of collision. But at this number of items, your probability of collision is at most 1/2. So you can pick a hash function from your random family. You can try this with reasonable probability. None of your keys will collide. And then you can hand back that hash function to your customer and say, here's the hash function. It'll work for your set of items. Okay? So the proof of this is the probability of some collision is the probability of the sum over any pair of balls, I and j, that they collide. They pick the same bin. Does the n choose 2 balls? This is the union bound. So I'm just, the n choose 2 is replacing the sum, and the 1 over m is replacing the probability here. Okay? So it says it's the most that, which is roughly n squared over 2m, which is roughly a half when m is 2n squared. Okay? Now, what's the problem with giving them this solution is now their hash table has to have n squared space, right? That's lots of space. I'm just hashing n items. I've given them a solution. I've given them pre-fixed, pre-built hash table. But the pre-built hash table uses n squared space to only store n items. Okay? So what if I want to construct a hash table with the order 1 lookup? Like maybe it doesn't, not almost collision free. So how do I do that? So what we do then is we do something hierarchical. We use the previous idea with an outer hash function. Okay? So we use a primary hash function which just maps to the range 1 to n. Okay? And now, at some point, if you take this hash function, just take a random hash function from your family, it's going to map a lot of items to the same entry. You'll have some collisions. So let's say n sub I is the number of items hashed to I. Like a lot of zeros will be here, right? There'll be a bunch of hash elements, a bunch of table entries will have zeros, but some will have a large n sub I. So now what we do is we choose a hash function that maps the universe to ni squared elements, right? That's what we did on the previous slide, the super inefficient thing. Okay, so now what I'm going to do is if I have some bucket that had 10 items in it, I'm going to allocate 10 squared space to it and do a subhash to that. Okay, and so that's what this is saying in notation. For a set of items, we can build in linear time a collision-free set. All we need to do is we pick a random hash function the first time, and if it's really bad, we throw it out, but it's not really bad. And now, for each of these buckets, we look at the bucket. We can pick a random hash function from our family here. We can see if it actually, with probability of half, it will succeed. So it won't take too long to find a hash function for each of the buckets. And so we can build this whole structure in linear time so that our final 2 hash sequence will lead to an empty square. Okay? And now the size of this thing is ni squared, right? Each one of the hash functions here is we have a table of the number of items hashed to that element, to that number squared. Okay. And now you need to show this is O of n with high probability. And this is a calculation. Each one of the ni's are random variables. Here's one analysis that kind of works. It says, what's the expected number of collisions? It's n choose 2 times 1 over n. We've seen this many times, right? That this is the number of pairs that could collide, and each one collides with probability 1/2 with a random hash function, with a universal family. And this is O of n. Okay? So the expected number of collisions is O of n, and you can use Markov's inequality to give that this happens with constant probability. Okay? But in fact, you can do it with high probability. But, okay, so are there questions? Okay, so this is a perfect hash function. So if somebody tells you, hey, these are the keys I care about, I need them all sort of minimal storage and really fast lookup time, this does it. Where you do a hash calculation and then another hash calculation, and that's it. Yeah. It's static in the sense that, yes, it's static, but it would work online too with reasonable probability. But getting exactly 1 is a bit of a pain, right? So this hash function that goes from ni squared to 1 to ni squared, it has only probability 1/2 of being successful. Okay, so if so some of your things won't be successful unless you check. So that's where we're using the static property. We're just hashing the keys and seeing if they collide. If they did collide, then we choose randomly a different hash function, and with probability 1/2, we will succeed. Okay, so that's where we're using the static. But you can also use it in some online fashion, and it'll have some properties, but not exactly the properties I said. Okay. Okay, so now the hash tables here were all pretty good. You could insert, you could delete, and you could also look up, right? So here I just want to insert or look up. Okay. So now I'm going to say you don't have to delete, you don't have to return the item. You just need to tell me whether it's in the set. Okay. That's all you have to say. So in the second thing, you're not looking up anything about X. You're just saying yes if it's in your set. Okay, and you're saying no if it's not in your set. Okay, that's the idea. So now we have to do less stuff. I don't need to return anything about the item. I just need to tell you whether it's there or not. Okay, and you want to preserve space. Okay. So now, actually, I say it at the end of the slide, but let me tell you now. Why do you want such a thing? Why would you even want such a thing? Like it's what we do as computer. It's just an index, right? So say I want to know some other computer somewhere far from me has a set of files. I want to just see if they have that file. And if they do have the file, then I want to go look there. I want to go send them a message, give me the file, right? So in these distributed systems, you don't want to send the message if you don't think they have the file, right? There's many, many computers out there, so you don't want to send too many messages and flood your network. So it's useful in that setting. You can make up some setting about menus at some restaurant. You don't want to go to the restaurant but you don't want to look at the menu because it's too long to read or something, I don't know. But we want to preserve, that's a stupid example. But it really is used everywhere in databases. Okay, so it's used in many, many contexts. This table, what does it contain? Which keys does it contain? Without actually, so you hand it over a very, very small object you hand out the small object, and that small object really contains information about some huge universe of items that are contained there. So that's what I mean by little o of n log u. Like this universe could be huge. Okay, so now you can't possibly do this. This is not doable, right? I'm asking you to use it in information theoretically. You can't answer these questions, right? I'm not allowing you to use enough space to tell me the answer. Okay, so something's going to break, and so what we can say is I'm allowing you to say yes, I have the item. You did insert the item. Okay, that's a false positive. When you didn't, that's a false positive. Okay? Now, a false negative is I'm not allowing you to say no if you do have the item. So I'm not allowing that. No false negative. You can't say no if the item has been inserted. You can say yes if the item wasn't inserted. So what's an easy algorithm for this? Yes. Yes is an easy algorithm for this, right? Very easy. Yes. I don't have to do anything. Very low space, great complexity, right? Okay. So it has a lot of false positives. Okay, there's a problem here. So we want to reduce the false positives. That's the game. That's what I'm going to do next, right? Show you how to build a structure that reduces the false positive. Okay? Okay. Yeah, it has a lot of uses. Does some database over there have this item? You want to have a very, very small representation of that database. So you don't want to go over there too often. Okay. Okay, so this is a Bloom filter. So once again, you have a table, and the entries are true or false. So this is like the 1-bit version of a Bloom filter. Okay, so you have a hash function from your universe to the size of the table. You initialize it to false, all the entries to false. So now nobody's in your set. That's what that means. All the entries being false means nobody's in the set. You haven't inserted anything. Okay. So now if you insert something, you do the obvious thing, right? You set the table entry corresponding to the hash value of x to true. It's fairly obvious. And you look up, you just return the value there. Okay? So are there false negatives? No, right? There can't be any false negatives, right? If I inserted the item to there, the bit corresponding to that item is set to true. And what will I return? I'll return that bit, which is true. Okay, so there's no false negatives. M is the size of the table. He asked, what is M? And he didn't know, so I said, no, I'm joking, maybe no. Okay, so there's no false negatives. T of h of x is true if x is inserted, right? That's the idea. What does it mean to be an element of set? You had to be inserted. So if you're inserted, that table entry is true. You never set anything to false, so it will always be true. Okay, so you're using up the falseness, right? Can there be false positives? Yeah. When is there a false positive? We've seen this over and over again, when there's a collision between two keys. Okay? So that's what we want to bound. We want to bound, once again, the notion of when do we collide and how often do we collide. Okay, so h of y is equal to h of x with probability 1 over m, assuming we're using a universal hash function, right? That's exactly the property of a universal hash function. If we choose h at random from our universal class, no matter what x and y are, these things are equal with probability 1 over m. So there's n minus 1 other items in the table at most. We're assuming some upper bound on the number of other items. So the probability of a false positive for x is less than, this is the union bound again. We'd multiply the number of bad things that could happen times an upper bound on the probability of a bad thing. So that's n minus 1 times 1 over m. And we get that the probability of the false positive for x is 1 over m, n minus 1 over m, which to my eye looks like n over m. So, okay? So how might you improve this? How might you get this? You want to make this small. What might you do to make this small? There's this m, right? You make m bigger, right? It's just sort of the obvious thing. They're less likely to collide if the table is bigger, right? So that will decrease, as you increase this value, m, you will decrease the probability of failure linearly, right? Okay. You could also kind of do many times, right? You can do this sort of many times. Okay, and then if you do it many times, you can sort of improve exponentially. right? You see, when you have failure probabilities, if you multiply one failure probability by another, you get squared of the failure probability. And if it's less than 1, it starts going to 0 exponentially. Okay? So let's see how to do it many times. Tables 1 through m that are true or false. You have hash functions, many hash functions. You initialize them all to be false. You set all of them to be true. Now for x, when you insert x, you don't only set the one hash function value to be true. You set all of these values to be true for all the hash functions. Okay? Then you return, when you return the and of all these values. Now you can already see where you might win. What for a false positive, right? If even one of these values is false, what is the and of all of these? Right? If even one of these bits is not set, the and of all these is false. Okay? So there's still no false negatives, because if you did insert x, all of these are set to true. We'd set them to true, so this and function will be true. The problem here is false positives, right? If somebody else, if x is not in your table, and yet somebody else is, many other people have set bits to be true. If all of these bits are true, then there's a problem for x. So that means there exists y1 through yk, where all of these values are equal to h1 of x, right? h1 of x is equal to h1 of y1, that should be y1, and hk of x should be hk of yk. Okay? So now that we already saw in the previous slide, for these hash functions selected from uniformly, from universal hash functions, you get, there is a yi such that hi of x is equal to hi of yi is less than or equal to n over m, right? That's just a calculation we did before. So now you just get to raise this probability to the k, right? And hash functions are, and the reason you get to raise the probability to n over k, to this failure probability, n over m to the k, is that the hash functions are chosen independently. h1 is chosen independently from h2, which is chosen independently from h3. Okay, again, it's the hash function that's chosen independently, not the keys. Okay, the analysis in the notes gives you a little bit better bound, but essentially with that bound, it says if you want to get the failure probability to be 1/100th, you need to get this m to be about 10 times n. If you did the linear scaling, you would need it to be 100 times n, or 200 times n. Okay? So this repeating independently is a better idea. Okay. So now, okay. Okay, so what should queries do? So first, when you're asking for documents, you want to say a document like this one. Okay? What does it mean for two documents to be similar? Yeah, what is similar, right? What is similar even? Okay, it contains the same words, right? That's sort of the idea for documents, right? So you have some universe of documents, and you want to say which ones are, for now, let's just think about which ones are similar instead of all the whole query and how do you return them and how do you build Google and all that stuff. But one part of it is what is similar, okay? So it says two documents are similar, or two web pages, whatever you want to call them, if they contain the same words. So a similarity measure for document X and document Y, they both contain words, right? So you say the words in X, if they have a lot of words in common, the numerator here is the words in common, and the denominator is the words in the union. Okay? So if they're the same document, what would this number be? Right, so it's a number between 0 and 1, right? The intersection of these two things is always less than the union. Okay? Okay, so this is called Jacquard similarity. Okay, so this is a notion of similarity. So it's fine. You can compute the similarity of documents, right? You can look at all the words in X, all the words in Y. You can take the intersection. You can then divide by the union, right? So this takes a while, right? Does that make sense? So any pair of documents, you would want to get the whole text and do this whole calculation, right? Now, is there a better way to compute this similarity, a faster way? So again, what we want to do now is instead of writing down, sending documents around and doing this comparison, what we want to take a document and we want to reduce its size to just something very small. And then we want to take Y and reduce the size to something very small. It's like hashing again, right? And the trick is going to have to do with hashing, okay? So we want to make them very small. And now from these small signatures, we should compare those signatures or these fingerprints of the documents. And then from that, we should be able to recover the similarity. Okay? Okay, so it's sort of a signature for documents. So here's a signature. Here's a proposed signature. So of all the words in the world, you pick a random permutation of this universe of words. Now, how you implement that, that's all something you can do. But so for animals, the universe of words is maybe you're just trying to see how similar they are with respect to animal words. And then you can put animal words up there. Okay? So you just take a random permutation, and for some reason horse came first and aardvark, and it's not alphabetical. It is what it is. It's some permutation. It's random. Now my hash function for a document is you take all the words in X, all of them, okay? You see where they are in this ordering, okay? So maybe the document X contains dolphin, and it also contains a bunch of other words that come after in this ordering. But it doesn't contain horse, aardvark, or jellyfish. So the first word that X contains in this list is dolphin. Okay? So you output dolphin. That is your digest. So the way I'm summarizing this document X, which has many, many words in it, is we take all of those words, we see where they are in this ordering, and we pick the first one in this order. Okay? It's a weird thing to do. Okay, so if X is about ocean, maybe dolphin. The output of this thing is a word. In fact, it's not even a word. It's an index into this permutation. Okay? So it's a dolphin is H pi of X. Okay. Okay, so that's the first word. So that seems like a really, now I've taken a document with possibly millions of words and just produced one. That's my signature or fingerprint. Okay, so documents X and Y. JXY is, remember, this is what we want to approximate, the similarity measurement. It seems fairly natural. I take a random permutation pi of V. This is my, my signature. Okay, this is my signature or fingerprint. It's called a fingerprint in the text. Okay, so what we want to do is let's just think about a thought experiment. Like remember, I want to model this thing up there, this J of XY. I want to figure out for Y, for X and Y, this measure, this Jacquard coefficient. Okay? So what I'm going to do is I'm going to check whether this H pi of X is equal to H pi of Y. They're both one word, right? If they both have dolphin in it, for example. Okay? So what is that going to do? That's going to answer yes or no, or which may correspond to the numbers 1 or 0, which is not going to correspond to that number, right? That number is going to be some number between 0 and 1, typically. But let's just think about the behavior of this test. What is the behavior of this test? Well, when you talk about the behavior of the test, it either answers yes or no. It's a coin. The behavior is P. What is the probability it answers yes? Right? That's when you flip a coin, the only question about the coin is what's the heads probability? Right? So for this one, I'm just making up this test and I'm saying, okay, what is the heads probability of this test? What do you think it is? It's on the slide. It's the first thing. It's J of XY. Right? The probability of passing the check for documents of X and Y is J of XY. Okay? So it's an estimator for J of XY, right? It's the number of words they have in common. So one of those words will randomly be the first word, with probability the number of words they don't have in common out of the total words. Right? The first word is equally likely to be, what's the likelihood, the first word in both documents? Will be the first one. The first word is equally likely to be in the first set. The probability it's in the first set out of the whole set is the size of the first set, the numerator over the denominator. Okay, the first word could be any one of these words in the denominator, and the probability it's one of the words in the numerator is just the size of that set. Yeah. No, there's no permutation in that, right? So all I'm asking is, what's the earliest word in this union? Okay, that's what we're asking, right? And now, if the earliest word in this union is in both sets, this is going to be equal. That's all, right? Okay, so now it's an estimator for a j of xy, but this test does nothing, right? It either answers yes or no. What I'm looking for is a number between 0 and 1, which is the heads probability of a coin. How do I check the heads probability of a coin? I flip it a lot of times, and I look at the long run average, right? Does this sound familiar? Yeah. Just like a poll, just how you do a poll. We saw all these polls in the elections. Okay, no PTSD, please, about the elections, but it's just like all those polls we saw before the election. We just keep asking for that. So the full fingerprint for these Descartes indices is you pick k random permutations, right? And then you check what's the number of agreements. And this is the heads probability of this coin. Okay? And analysis from 70 says this gives you this gives you a 1 plus epsilon approximation to the similarity measure. Okay? Okay. We'll see you on Thursday.